As we saw in our previous video, materials have a significant influence on the fire hazard that a shelter poses to its neighbour. Whilst our experiments included several different combustible materials, thatch stood out on its own as particularly hazardous. Understanding how thatch or thatch style materials burn is critical for fire safety in any environments in which they are used as a building material. In this video, we examine the fire spread hazard of thatch and why it burns so intensely. If you have not already watched the first film in this series, go back as we explain how we measure the rate that energy is being released and the equipment we used to capture this.
Our first test was terrible. Everything was broken, and then once we go into the swing of it, we're upwards of 97% success rate on the instrumentation, I would say.
One method of understanding the hazard that the fire presents is to quantify its heat release rate. This is simply the rate at which the fire is releasing thermal energy, and it correlates to the rate of mass loss during burning. Here we will focus on key findings from the mass loss data of various of our experiments. As a benchmark for comparison, let's start with the mass loss rate of a basic compartment fire with non-combustible walls. Each of the cement block, mud, and metal sheet wall shelters with a metal sheet roof reached a mass loss rate of 0.5 kilograms per second. That is, for every second of burning, half a kilogram of solid fuel is being converted to gas, consumed in the fire, and then released as thermal energy.
I think the wind is having a big impact because it seems like the hot gases are venting so much.
But it took a while to flash over, right? Because no part of the structure is burning.
When the shelter had combustible facades, either walls or roof or a combination of the two, the mass loss rate would increase because there was more fuel to burn. Most experiments, such as this bamboo mat and thatch shelter, produced and burned fuel at a peak anywhere from twice as much to 4 times as much as a non-combustible compartment fire. But one experiment was the runaway leader for mass loss rate. Made from thatch walls and a thatch roof, this shelter at one point was releasing mass and therefore thermal energy at a rate 8 times higher than the non-combustible compartments. It is easy to see how so much gaseous fuel is being produced by seeing the extremely tall flames that are emitted from the top of the shelter. We estimate these are over 5 meters tall.
It depends whether the wall or the roof has gone first, and the roof has gone easily first because there's obviously it caught fire and there's a lot of hot gases. But it means really that rather than everything projecting outwards, we've this huge flame plume upwards.
Fuel consumption is a useful indicator of how much of a hazard the fire might pose, but it is not enough in itself to show how the fire might spread. In the thatch experiment, the very intense burning that is indicated at by this really high mass loss rate then also results in conditions of very high fire spread risk, which shows on our instrumentation. The fire inside the shelter recorded temperatures over 1200 degrees Celsius at many locations, and we know that emitted thermal radiation increases dramatically with temperature. This was clear from our heat flux gauges, which were located 2 meters away from the door and window. The data from the gauges help us to understand how quickly any nearby combustible materials will ignite. In the thatch experiment, the gauges at both the window and door were exposed to heat fluxes in excess of 60 kilowatts per meter squared. This is 2 or 3 times higher than in most other experiments, and roughly 5 times the level needed to ignite wood. Although other experiments did show similarly high heat fluxes, it was always because of brief moments of flame impingement, only occurring for a few seconds here and there. The thatch shelter was different because there were no flames projected from the door or window. The high heat fluxes persisted for several minutes. This showed that thatch shelters have the potential to generate and distribute huge amounts of thermal energy to the surrounding area without necessarily relying on direct flame contact. But why is this the case? What we call a thatch style material is simply a bundle of individual thin elements of some material, usually reeds, palm leaves, or straw. Our experiments used reeds that had been harvested nearby in the Western Cape of South Africa. However, the following theory should generally apply to all thatch style materials. Compared to a solid bulk of combustible material, such as timber, the individual pieces of thatch are much thinner and easier to ignite. Once burning, the bundle of thatch has a much larger surface area to volume ratio than a piece of bulk solid material. Fuel gases can be released from the entire surface area of each thin individual element, rather than just at the surface of the overall bundle. So much more fuel gases can be released from the material as a whole compared to a bulk solid fuel. And finally, as layers of thatch burn away rapidly, the pieces behind are more easily exposed, giving fresh material to be burned. Compared to solid bulk fuels, which form a char layer that limits the ingress of heat into the material. These factors combine to make thatch style materials burn away rapidly when used as a shelter facade.
It was hot, man, it was hot. So we probably lost quite a lot of instrumentation from radiation. What we didn't actually have a lot of that we did in other tests was flame impingement, so we didn't have big flames shooting out sideways, hitting rigs. So it'll be very interesting to see the heat fluxes we get around and compare that to whether, like, it'll be pure radiation basically, because there's not like hot gases flowing over it. It'll be purely radiation from those big flames. Like at this.
Our experiments show that the shelter entirely composed of thatch constituted the most extreme fire spread hazard, despite not resulting in flames being projected from the door or window. Generally from this and other experiments with thatch roofs, and for the reasons discussed in this video, we can see that fire establishes very quickly on thatch facades, burning fuel at a much higher rate than other combustible materials. It is therefore important to acknowledge thatch style materials as a unique challenge for tackling fire spread. Another challenge when tackling fire spread is wind. Watch the next video in our series to find out how some of our experiments were impacted by wind and what we can learn from those experiments.